Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss calculating powers of matrices. So in this topic we will discuss calculating a matrix raised to the power k times a vector u0 for different values of k, including potentially, if the matrix is invertible, for negative powers of k. We will see how using an eigenvalue decomposition aids us in this calculation. We will observe that this will result in fewer computations and therefore will be both faster and have less numeric error. We will see that we can use this approach even if the matrix A is not self-adjoint. That is, it is not symmetric if it is a real matrix, and it is not conjugate symmetric if it is a complex matrix. Because, as you will recall, if it is not self-adjoint, the matrix of eigenvectors is not going to be orthogonal or unitary. Now, in some situations, a matrix may represent a transition from one state to the next. So if A is such a matrix, for example, it may be a stochastic matrix, that is where either the sum of the entries of each of the columns is equal to 1, or the sum of the entries of each of the rows is equal to 1, or if it's a divided difference matrix, in which case it represents an approximation of a differential equation. Anyway, in each of these cases, if A is such a matrix and U0 is the initial state, then we can find the next state by simply multiplying U0 by the matrix A. So U1 is assigned A times U0. Now, in general, if U sub k is the current state, then the next state is simply the current state multiplied by the matrix A on the left. So U sub k plus 1 is simply assigned the value of A times U sub k. Now, alternatively, we could make a direct calculation. We could simply, therefore, calculate the matrix raised to the exponent k, multiply that by the vector u0, and that will give us directly the vector u sub k, that is the kth state after the initial state. There are, however, some issues with these approaches. Well, first of all, calculating a matrix exponent exponential is expensive. Raising a matrix to the power n is something you generally would rather avoid. Also, there's going to be very many floating point operations occurring here. So numeric error can quickly build up, and we are not able to mitigate most of these. You'll recall that with Gaussian elimination, we introduced partial pivoting to mitigate some of the effects of numeric error. However, there's nothing we can really do here. Now, suppose that A can be diagonalized, and so I'm just assuming A can be written in the form U times a diagonal matrix D times the inverse of U. And you'll recall, if this is possible, the matrix D contains all of the eigenvalues on the diagonal, and the matrix U is comprised of the corresponding eigenvectors which are normalized. So in this case, we note that if we calculate A squared, well, that's just the square of that product. But that's just multiplying those three matrices by themselves. But matrix multiplication, as you'll recall, is associative. If I'm multiplying 6 matrices together, it doesn't matter which order I multiply them in. So I can actually explicitly choose to multiply first U inverse times U. But wait a second, U inverse times U is just the identity matrix. Consequently, this equals U times D times D times the inverse of U. And that's just U times D squared times U inverse. But wait a second, D is a diagonal matrix. So the diagonal matrix multiplied by itself is just the same diagonal matrix with each of the diagonal entries squared. Now, this gets even better, because if A is equal to U times this diagonal matrix times the inverse of U, then it follows that A to the n is U times D to the power n times U inverse. But raising D, which is a diagonal matrix, to the power n is equivalent to just simply raising each of the diagonal entries to the power n. What are the benefits of this? Well, in this case, calculating a diagonal matrix to the nth power is trivial. All we have to do is calculate the eigenvalue decomposition and then raise each of the diagonal entries to the power n. That can be done very quickly. There's even an added benefit. If all the eigenvalues are non-zero, then the matrix is invertible. And we can even calculate the inverse simply by finding that diagonal matrix that has the reciprocal of all of the eigenvalues on the diagonal. And you will recall that a matrix is invertible if and only if all of the eigenvalues are non-zero. Therefore, because the reals or even the complex numbers are a field, we simply need to calculate the reciprocal of each of them. For example, consider the following symmetric matrix. Of course, if it's symmetric, therefore it has 5 eigenvalues, it's diagonalizable, therefore we can find an eigenvalue decomposition, and on top of that, the matrix U will be orthogonal. Let's calculate a to the 10 times this initial vector U naught. Now, using an appropriate software package, whatever you're using, we can find that A is equal to this matrix of eigenvalue vectors, a matrix of diagonal matrix where the eigenvalues are on that diagonal, all of this times the transpose of that first matrix. Of course, the transpose of the first matrix is the inverse because it must be orthogonal. Consequently, we can now easily calculate the diagonal matrix raised to the power 10 simply by raising each diagonal entry to that power. This is something that can be done very quickly. Therefore, if we want to calculate a to the 10 times this initial vector, all we need to do now is multiply that vector by the transpose of the matrix U times that diagonal matrix times the matrix U. Doing so gives us the following vector. All right, that's all there is to it. Now suppose that we don't just want to calculate a to the k times an initial vector u naught, but rather we'd like to calculate a to the k times u naught for many different values of k. In this case, suppose we wanted to calculate u naught through u10, therefore having to calculate a to the k times u naught for k going from 1 to 10. Question: do we just calculate u1 by multiplying u naught by a, and then calculate u2 by multiplying u1 by a, and so on and so forth until we get u10, which is assign the value of A times U9? Or alternatively, do we use the eigenvalue decomposition, and therefore U1 is just this product, U2 is a similar product, but now we are using D squared, and we'd carry on all the way up until U10, each time calculating U sub k by calculating U, the capital matrix U, times the diagonal matrix raised to the power k times the inverse times the vector U0. Well, issues. For example, there are many different calculations that are involved when we are calculating the next entry if we are doing this iteratively by calculating U1 and from that calculating U2 and so on and so forth. Each matrix vector multiplication introduces errors, but not only that, the previous value that we are using now also has errors associated with it, and therefore those errors are going to be magnified. On the other hand, if we use the eigenvalue decomposition, calculating the diagonal matrix raised to the power n is easy and also relatively free of error for all possible values of n. So therefore this suggests that even if we wanted to calculate all of these results, it still makes more sense numerically to use the eigenvalue decomposition. Now, we've already mentioned before, don't calculate the inverse unless calculating the inverse is straightforward. So for example, the inverse of a diagonal matrix is that diagonal matrix with the reciprocals of the diagonal entries of that first matrix. That's easy to calculate. Also, the inverse of an isometric operator is its adjoint. Again, for a real orthogonal matrix, the inverse is the transpose. And for a complex unitary matrix, the inverse is the conjugate transpose. Question: what do we do if we have an eigenvalue decomposition, which we've found with a computer, for example, you're running some software, and we get that we have an eigenvalue decomposition, but the matrix is not easily invertible? Now, fortunately, we can still perform these calculations without an explicit calculation of the matrix inverse. So suppose that A is not self-adjoint. That is, if A is a real matrix, it is not symmetric, and if A is a complex matrix, it is not conjugate symmetric. In this case, if we wanted to calculate a to the n times some vector u, and let's say this result is the vector v, then assuming that we can find an eigenvalue decomposition, that is, we can diagonalize the matrix, we can then perform the calculation as follows. The vector v is equal to the product of the eigenvector matrix times the diagonal matrix of eigenvalues raised to the power n times the inverse of the eigenvector matrix. All of this is times the vector u. However, using associativity, we can rewrite it as follows. First, calculating the inverse of the eigenvector matrix times the vector u, and then, and only then, multiplying that by d to the n times the matrix of eigenvectors. Well, in this case, we don't want to explicitly calculate the inverse of the eigenvector matrix. So let y equal the inverse of the eigenvector matrix times the vector u. Well, if we multiply both sides by the eigenvalue vector matrix, then we get that the eigenvector matrix U times Y is equal to the target vector U, which we already know. Y is the unknown. So all we have to do is solve a system of linear equations for the unknown vector Y. With this, we can then calculate that vector Y, which we found, times the diagonal matrix raised to the power n times the matrix of eigenvectors. Following this topic, you now understand how to use the eigenvalue decomposition, that is, diagonalization, to calculate a to the k times some initial vector u for different values of k, assuming, of course, an eigenvalue decomposition exists. You understand that this is going to result in answers that are more accurate and often require fewer computations, especially in the case where we only want to calculate the occasional power of the matrix A times the vector U. You also understand that, as we saw previously with the PLU decomposition, we can still calculate this without explicitly calculating the inverse of the matrix, by instead converting the inverse of the matrix times a vector to a system of linear equations that must be solved using Gaussian elimination and backward substitution. In fact, you could indeed use PLU decomposition once you calculate the eigenvector matrix U. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!